Alright, so now let's do an example with the basic ideal Brayton cycle. So in this case, I've got a simple air standard Brayton cycle. It's operating between 1 and 5 atmospheres, which is roughly 100 and 500 kilopascals. So a significant pressure increase. But this is really what I said would be the minimum value of R sub P. Now the inlet air to the compressor is 80 degrees Fahrenheit, which when I'm working these problems, because I'm assuming ideal gas law is going to require 540 degrees R. I either want to use kelvins if I'm in SI or degrees R if I'm in engineering type units. I'm going to take this so that the turbine inlet has been heated in the combustion step to 2040 degrees Fahrenheit or 2500 degrees R. And what I want to know is what is the efficiency of the cycle. So the given information is that the low pressures, which are states 1 and 4, are 1 atmosphere. The high pressures, states 2 and 3, are 5 atmospheres. And the temperature at the very beginning, state 1, is 540 degrees R. And at state 3, the inlet to the turbine or the exit from combustion is 2500. So now we need to go gather data. If I have just as much as temperature, that's all I really need, I can go to those ideal gas tables, find one in engineering units, and look up those pieces of information. Now in this case, because it's flow, I need H, and PR is going to help me out when I start doing isentropic calculations, and S naught if I need to calculate any entropies. Also, I want to talk about that and whether or not I'm actually using the constant entropy assumptions properly. So as I do this, I looked up the data for this first state, and I looked up the data for this next state, and in the tables I was using, these are the values I had. Then I can use the pressure ratio. Remember, PR2 over PR1 equals P2 over P1, which means I can take this PR1 I have, multiply by 5, because the pressure increased 5-fold, and that will get me PR at this state. Similarly, steps 3 to 4 are isentropic, and so P3 over P4 is PR3 over PR4. So from this value to this, I would divide by 5. So I found this state, state 1 and state 3, using the given information. And now I'm going to use my fact that I have isentropic processes to determine one piece of information for state 2, one piece for state 4. I already have pressure information about those. So now I have 2 pieces of data. I can now go, based on PR, I can find everything else about states 2 and states 4. It does require interpolation, but I'm only having to interpolate in temperature ever. Okay, so the temperature in between is 852. By the time it exhausts, it's 1681. I have pressure values here. Now I said that these are constant entropy processes, but notice that the S naught from the table are not the same, but these are indeed the correct numbers. The reason that they're not the same is because this doesn't include the pressure correction. If I want the pressure correction, I either need to do that ratio PR2 over PR1 equals P2 over P1, or I need to subtract off R ln of P2 over P1. So now I have the data, we're ready to start analyzing the problem. The efficiency is the work of the compressor, so H1 minus H2, the work of the turbine, H3 minus H4, divided by the heat transfer for the combustion phase, H3 minus H2. So my net work is 153 BTUs per pound mass. My heat transfer in is 441 BTUs per pound mass. My thermal efficiency is 0.346. Now, for the sake of argument, what if I calculated this efficiency using cold air standard? I'm using a value of 1.4 for K. My pressure ratio is 5. I get 0.369. So before, what was it? 346. Now 369. So you see that it's not going to be exactly right, but it's going to get me a ballpark figure, which allows me to evaluate whether all that work I did was appropriate, getting me good values, whether I'd inadvertently read something incorrectly from the tables, made some major assumption, problem early on. I can actually use this very quickly. Now, just for sake of comparison, the maximum thermal efficiency would be if it were a Carnot cycle. Carnot cycle says take TL over TH, subtract that from 1. My low temperature here is 540, my high temperature 2500, subtracted from 1, I get a ratio of 0.784. Now, one way I can analyze this is through a second law efficiency where I compare this to this as a ratio, and I'm at 44%. Okay? Now, there are several things, and you'll have to go back to look at the Rankine cycle examples we had done in class to convince yourself of this perhaps. But there's sort of a general truth that in general, if I have a Brayton cycle and a Rankine cycle, usually I can get a higher efficiency out of the Brayton cycle. Just the way that we're driving our compressor and our turbine, compressing in gas is not so hard. It really turns out I really do pretty well here in terms of thermal efficiencies. I'm going to expect larger values, okay? But I also am using higher temperatures. So the maximum, the Carnot efficiency, is always going to be higher. So the temperatures of a Brayton cycle end up meaning that I have higher Carnot efficiencies, which means that the ratio of my Brayton to my Carnot efficiency for the Brayton temperatures is usually actually lower than what I do for a Rankine cycle. I usually can get more like 2/3 of the way towards the Carnot efficiency with Rankine. It is a better use of our resources. So at this point I'm going to pause. We're going to come back and do a variation on this where we look at what happens if I introduce reality and process efficiencies.